Hi, my name is Haitong Ni, and today I'll be presenting the paper, A Hybrid Posture Detection Framework, Integrating Machine Learning and Deep Neural Networks, which was published in the IEEE Census Journal in 2021. And first, we'll look at the technical framework, a deep dive into the models and implementation. So let's start with the fundamental challenge this paper addresses. Why is this research important? First, as the slide says, we face rising health and resource burdens. We have an aging population that requires more remote monitoring, and we have widespread sedentary lifestyles that lead to chronic health issues. And this creates a clear and urgent need for automated health tracking technology. Second, the inadequate accuracy of existing methods. While many posture detection systems exist, they often fail to achieve the high reliable accuracy needed for medical and real-world applications. And this is the technical gap the authors are trying to solve. And this slide shows a simplified view of their entire system. The original paper's diagram is quite chaotic, so I've simplified it into this three-stage flow. First, raw sensor data is collected. And second, this data is fed into two parallel pipelines. Each different machine learning models are fed handcrafted features, and four different deep learning models are fed into raw data, and also the handcraft features. And this creates a committee of 12 base learners. And third, this is the key innovation. The predictions from those 12 models are collected and used as new features. And a final meta-learner is then trained on these predictions to make the one final, more accurate decision. And before we look at the models, we must understand the data. The entire experiment is based on an online benchmark dataset. It uses a non-visual galvanic skin response sensor. The data was collected from only 5 individuals, or aged 25 to 30, and is used to classify 3 simple postures: standing, sitting, and walking. And so, here is the full manual of all 12 base learners used in phase 1. The exhaustive brute force comparison is a major part of the paper's engineering contribution. For the machine learning pipeline, they first extracted 6 statistical features like mean, curtices, and skew, and they fed those features into 8 classic machine learning models, including SVM, KNN, random forest, and logistic regression. And in parallel, for the DL pipeline, they used 4 distinctive models: 1D CNN, a 2D CNN, an LSTM, and a bidirectional LSTM. And crucially, they trained these models on both the features and the raw data to see what works the best. Now, let's do the technical deep dive that the paper itself should have done, and this is where we prove our understanding. This table is one of only 2 architectures the authors provide. It's their 10-layer 1D CNN. Let's work through it. Data sequence comes in, it hits the first convolutional layer with 16 filters and a kernel size of 3. And this finds very simple local patterns. And this is immediately followed by a max pooling layer that downsample the data and keep only the most important information. The compo block repeats, but the network gets deeper. The next block has 32 filters, then 64, then 180, 128. And this design is classic. the network is forced to learn progressively more complex and abstract feature combinations at each stage. Finally, at the last convolutional layer, a global max pool layer flattens the entire sequence and is fed to two fully connected layers for the final softmax classification. The only other architecture they detail is this one, which they confusingly call an LSTM in the text. As we discussed, this is actually a stacked bi-LSTM or bidirectional LSTM. A standard LSTM is unidirectional. It only processes data from the past to the future. And this architecture is bidirectional, which is a critical choice from posture. It uses two stack LSTM layers, one with 180 cells, the other with 64. That processes the data both forwards and backwards in time. This is essential because of posture, like sitting down, is defined by the movements before and after the main action. It is stacked because the two layers allow it to learn higher level temporal abstractions. And finally, a dropout layer is used to regularization, and a dense layer with softmax makes the classifications. So we have our 12 base models. How do we combine them? And this brings us to phase 2 and the stacking technique. This is the 3-step progress. First, they train all 12 base learners on the datasets using tenfold validation. And this is a crucial, rigorous step. It means they train on 9 folds and get predictions on the 1 header fold and repeat this 10 times. This ensures the predictions are unbiased. Then they collect all these held-up predictions. This creates a new dataset where the features are the 12 predictions from the base models. Finally, they train the new model, the meta-learner, the hybrid one, on this new dataset. In essence, this meta-learner's job is to learn which of its 12 employees to trust. It learns for this type of data, the CNN is usually right, but the SVM is wrong, for example, and it weighs its final decision accordingly. Before the final results, the paper reveals a key finding. They tested their deep learning models on handcraft features versus raw data. As you can see at the left part, the 1D CNN's performance on any handcrafted features was worse than when it was fed raw data. And where it achieved accuracy of 94.56, this confirms the hypothesis. Deep learning models perform best when allowed to find their own features. Simultaneously, we know from the paper's tables that the best machine learning model, a logistic regression, needs all 6 features to achieve its top score of 95.98%. And this sets up the perfect justification for the hybrid model. This brings us to the money slide, the final result. The hybrid CNN model, when fed the predictions from the base learners, achieved a new state-of-the-art 98.14% or 98.14%. This results, this 98% is the entire engineering contribution of the paper. It proves that the hybrid stacking approach successfully outperformed the best standalone machine learning model and the best standalone deep learning model. So, the results is impressive. But this is where our jobs as critical scientists begin. The work has significant limitations. First, the one they admit computational cost. The system requires training and running 16 models just to get one prediction. This is astronomically expensive and completely impractical for a real-time, low-power wearable device. And second, the one that should have been a red flag: data and generalization. The entire experiment was run on a dataset from 5 individuals. 5. This is a critically small, homogeneous sample. We have no confidence this model would generalize to new users with different ages, weights, or genders. It is almost certainly overfit to those 5 people. Now we move to the severe scientific flaw. This paper is non-reproducible. As we discussed, the authors test at least 8 different deep learning models, the 4 base models and the 4 hybrid models. And yet, they only provide architecture details for 2 of them. And we have no information for the other 6. We don't know the 2D CNN architecture. We don't know the base LSTM architecture, and we have no idea what the 4 hybrid meta-learner models look like. And are they the same as the base models? This paper simply doesn't say. And the conclusion part is just a simple comparing of the final numbers, lacking deep analysis on why the hybrid model works. And here's the worst part of this paper, the writing quality, which is where the foundation of trust begins to collapse. The paper is fundamentally flawed in its writing. It is really, really difficult to read, not because the ideas are complex, but because the communication is careless. It lacks logical flow, and it is riddled with innumerable typos and factual errors. As you can see in the screenshot, the most famous error from this paper is in Table 1, where it lists KNN and K nearest neighbors as 2 different algorithms. They are, of course, the same thing. And also, you can see in the other pictures, there are multiple basic errors. And these aren't just minor mistakes. It reflects significant negligence from the authors and on the peer review process. And it forces us to ask a critical question. If the writing is this careless, can we trust the unseen rigor of the code? To conclude, this paper presents a state-of-the-art result based on a sound engineering idea, the hybrid stacking model. However, this result is built on a foundation of severe limitations, including a tiny dataset, a non-reproducible methodology, and a level of carelessness in the writing that undermines its own credibility. Thank you.